So far we have discussed several recombination mechanisms in semiconductors. The ideal current voltage relationship of a p-n junction diode has been discussed also in one of the previous videos. In this video we will see how recombination and conversely generation will affect the current voltage relationship of a p-n junction diode. We will do this by looking in more detail at the generation and recombination processes in the depletion region of the device. Therefore, we will first look at the space charge region under reverse bias and derive a contribution to the current that is particularly visible in reverse bias, the generation current. Next, we will focus on the space charge region under forward bias and the more detail on the recombination taking place in that region. This recombination leads to the derivation of the recombination current. Finally, we will direct our attention to the ideality factor, which describes the behavior of a diode. We will start with the space charge region under reverse bias. If we have a p-n junction under reverse bias, we obtain a band diagram as shown in this slide. In this case, the Fermi level of the n-type region is well below that of the p-type region, significantly increasing the barrier for electron injection from the n to the p-type region. This in effect implies that hardly any current is flowing. In the depletion region, the bands curve strongly when moving from the p to the n-type region. The difference between the Fermi levels of the two semiconductor regions is equal to the applied reverse bias voltage VR. We now are going to look at the generation in the depletion region, and we do this via the back door, first by considering the process of Shockley-Reed Hall or SRH recombination in this region. We do not consider any other recombination mechanisms, as radiative recombination occurs mainly outside the depletion region and the carrier density in the depletion region is too small for Auger recombination to be significant. So we first take a step back and consider the recombination rate for SRH recombination again as is given by the following relation. We discussed this equation when I was explaining SRH recombination. In order to make an estimation of the generation in the depletion region, we will rewrite and simplify this relation somewhat. First, we focus on the emission coefficients En and Ep that we can see in the denominator. To get a somewhat better understanding of these coefficients, we revisit the rates of the different processes that govern SRH recombination. The first and the third process are related to the capture of charge carriers, whereas the second and the fourth process reflect the emission. Now we will consider thermal equilibrium. In that situation, we can apply the concept of detail balance, which states that the capture and emission processes must be equal. Using this concept and applying the Boltzmann approximation, the emission coefficients can be worked out. We then see that the emission coefficients are proportional to the reach of the trap, the effective density of states in the conduction and valence band, as indicated by the subscript C and V respectively, and an exponential term which relates to the trap energy ET. By assuming that the trap state energy is equal to the intrinsic Fermi level, so exactly at mid-gap, we can rewrite these two relations. The density of states times the exponential term is then equal to the intrinsic carrier concentration, resulting in the following two relations. We can now use the two relations to rewrite the recombination rate equation and define the constants Cn and Cp as the thermal velocity times the respective cross-sections. We then find the following relation, which now looks a bit friendlier. We will use this relationship to work out the generation current under reverse bias. What we in fact will be doing is to say that in a semiconductor in thermal equilibrium, the generation rate is balanced by the recombination rate. As we have an expression for the SRH recombination rate, we use this equation to make an estimation of the generation rate. Finally, we apply this equation to the situation in the space charge region. Now let's do it. We start with the equation for SRH recombination rate and simplify this equation further by using an important assumption. We can say that because of the strong electric field in the space charge region, the mobile carriers are swept out of the space charge region as soon as they are generated. As a result, the free charge carrier concentrations in the space charge region are equal to 0. After some rewriting, this leads to the following equation. Note that the recombination rate is negative, which means that charge is actually being generated. As we have seen before, the SRH lifetime is inversely proportional to the trap density and the capture coefficients, allowing us to rewrite this equation again. We now define tau 0 as the average of the lifetimes for electrons and holes, which then leads to our final expression of the recombination rate. Note that this recombination rate is equal to minus the generation rate. In this slide, we visualize the generation process in the space charge region. Because of the large electric field inside this region, the charge carriers move out of the space charge region, which means that we have an extra current component, the generation current. It may sound strange that we have used the SRH recombination process to work out the generation rate. However, since there are essentially no free charge carriers present in the reverse bias space charge region, electrons and holes are generated by trap states to re-establish the thermal equilibrium. Because the generated carriers are then removed from the space charge region by the electric field, the generation continues and the generation arises. The generation current density can now be calculated by integrating the charge generation inside the space charge region. By utilizing our previous result, we obtain a simple expression for the generation current. The total reverse bias current density is thus the sum of the ideal reverse saturation current density, Js, and the generation current density, Jgen. We have seen earlier the dark current voltage characteristics of an ideal p-n junction diode plotted here on a semi-log plot. Since the generation current density is a function of the space charge region width, which in turn is a function of the reverse bias voltage, the reverse bias current density is dependent on the reverse bias voltage, as can be seen in this graph. You can see that as we apply a larger reverse bias voltage, the current starts to deviate from the ideal reverse saturation current density because of the generation current. Now we examine the band diagram of a p-n junction under forward bias. In that case, the device is not in thermal equilibrium and we need to consider the quasi-Fermi levels. As can be seen, the quasi-Fermi levels of the semiconductors are offset by the bias voltage. When we look at the quasi-Fermi levels with respect to the intrinsic Fermi level, we can see easily that the addition of the energy difference between the quasi-Fermi levels and the intrinsic Fermi level equals the applied voltage, as expressed in this equation. If we now look at the situation at the interface between the p and n-type, the so-called metallurgical junction, we see that the intrinsic Fermi level is exactly at the center of the quasi-Fermi level for holes and the quasi-Fermi level for electrons. This changes the equation slightly. We now look at the situation at the junction for a good reason, because at this point the energy difference between the electron quasi-Fermi level and the intrinsic Fermi level is the same as the energy difference between the whole quasi-Fermi level and the intrinsic Fermi level, which means that the electron and hole densities at this point are equal. This is important because then the SRH recombination rate is maximal, as illustrated in this slide. Work this out for yourself. We can now use the equation we just obtained to calculate the recombination current, as you will see in a minute. First, we recall the expressions for the minority carrier concentrations as was derived in previous lectures. Note that part of the term in the exponents is the same as in the equation we just derived. This allows us to relate the minority carrier concentrations to the bias voltage. And we obtain a simple relation that describes both minority carrier concentrations as a function of bias voltage. It is important to note that this is only true for trap states at the center of the band gap. If this is not the case, the relations for the carrier concentrations will look somewhat different and, above all, are not equal to each other. When we again look at the recombination rate, we can simplify this for the forward bias case. We will not go through it step by step, but the steps are essentially the same as for the reverse bias case. This leaves us with the following equation, which is the maximum recombination rate in the space charge region under forward bias. Simplifying this equation further by assuming that the bias voltage VA is much larger than the thermal voltage given by K times T divided by Q, leaves us with the following equation. We can use this recombination rate to calculate the recombination current density in the same way as we calculated the generation current density, leading to the following relation, and we can simplify this by defining the term in front of the exponent as the saturation current for recombination. The total current density is thus built up out of two terms. We just derived the recombination current density given by this relation. The diffusion current density is given by this relation, which has a similar expression. We can see that both current densities depend exponentially on the applied voltage. However, there is an important difference, namely the factor of 2 in the denominator of the argument for the recombination current density. In general, the diode current voltage relationship is written as the following equation, where the factor of 2 is incorporated in the variable n. This n is called the ideality factor and varies between 1 and 2. When we plot the natural logarithm of the current densities versus the applied voltage, we obtain the following graph. Here you see the recombination current, which has a slope of 1 over 2, thus representing an ideality factor equal to 2. When we plot the ideal diffusion current, you can see it has a steeper slope equal to 1, implying that the ideality factor is 1. The total current density is the sum of the two and shows a transition where n varies between 1 and 2. We can thus state that at low forward bias n is equal to 2, while at high forward bias n is equal to 1. The latter is of course because the ideal current voltage relationship varies much faster with applied voltage. Before I conclude, I would like to make a remark about the ideality factor for the recombination current. You will see that in the field, often for analysis of the current voltage relationship of PN junction diodes, two components are used. A term based on the diffusion current with ideality factor of 1, and a term based on the recombination current with ideality factor of 2. Note, however, that an ideality factor of 2 is only obtained for a very specific situation, namely for a defect center in the middle of the band gap and at the metallurgical junction. In general, this is not the case, leading to an ideality factor in between 1 and 2. It is therefore important to be careful when making statements on the contribution of the recombination current when analyzing these characteristics in this way. Now let me summarize this video. We have discussed the generation current density and the recombination current density. Finally, we discussed the ideality factor, which shows a clear dependence on the applied voltage and varies between 1 and 2.